instead of having a number of lab tours and so on and so forth, we decided actually to have some panels where we actually can discuss some of the topics that is keeping a lot of our faculty busy. So we have two panels this afternoon, and we're going to first start with one which is on self-driving cars. It's on autonomous driving AI complete. So we have three panelists this afternoon, starting with Jitendra, Malik, or chair, Trevor, Darrell, and Anca Dragan. And with that, I'm going to pass it over to Jitendra first.
Thank you. Can you hear me in the back? Great. Okay. So the setup is we are supposed to discuss whether self-driving cars are going to happen in the near future. And in order to set up the stage for that, I decided that it's worth going through a history lesson. Because I've been around in this field for a while, and I had a self-driving car project 20 years ago. And there were people who had self-driving car projects 10 years before that. So self-driving cars have actually been around for 30 years. Okay? And sometimes it's one of these jokes which I've heard about gallium arsenide. It's one of these things which is the technology if 2 years from now or 5 years from now, but it remains that way forever. So we have to be aware whether we are in that kind of a situation. So there's this line that those who do not know the past are condemned to repeat it. So I'm going to give you a history lesson. Okay. So the first self-driving cars. Okay. So the first projects on mobile robots go back to, say, the 60s. And, but the first self-driving car project was done by this guy, Ernst Dickmanns. This is the guy in the suit and tie. He was a German at the university, the German University of the Army, University of Bundeswehr in Munich. Actually, I'm curious, how many people in this audience knew of Ernst Dickmanns before I talked about him? Okay, that if there is one thing that you take away from the end of this talk is that this is the man who actually invented self-driving cars. But of course, there will be 15 inventors before it's done. But this is the guy who did it first in Germany. So his idea was that, in fact, we can think about all the complexities of driving, but if you focus on driving on the Autobahn, the German freeways, then it's really about a simple control problem. Stay within your lanes and avoid hitting the guy in front of you. That's it. So it's a fairly simple problem once you think of it that way. There's a parameter which measures the position of the car with respect to the sides of the lanes. And then there's another parameter which measures the distance in front of you. So we're talking about three numbers here, right? Control theorists know how to tweak, how to do things such that those numbers are kept at the right levels. End of story. That's what self-driving is about. And he had cars driving on the freeway in Germany in 1988. Okay, 1988, with some Intel chip, must have been Intel 4040, 8080, something of that type. Okay, we always talk about Moore's law forward. To make sense of this work, you have to talk about Moore's law backwards. So it was 30 years ago. So therefore, computers were 1 million times slower. And that's when you had to get self-driving cars to work. Okay, so that's that. In the 90s, there were multiple groups which had projects on self-driving cars. CMU was very significant. In the US, it was CMU who pioneered first a very AI type approach and then a neural network type approach. I'm going to show you a bit of that. And then we at Berkeley, we had a very control theory type of approach. There were multiple projects, and down to the stage that the federal government, NHTSA, National Highway Traffic Safety Administration, it decided that this was a way you could improve the fatality rate. So in 1997, they had this demo, And the goal of everybody, all of our groups which were working on this problem, was that we would have a demonstration on how there could be self-driving cars in 1997. Okay, and that was supposed to be the culmination of all the research up till that point. So, so here is a little plug for our project, which was a comparative study of. Okay, let me put up Dickmann's slides, because Dickmann's alternated between this view of what was needed to get sort of like 95% autonomy to what was needed for getting 99.9999999% autonomy. And those are quite different problems. The 95% problem is actually quite easy. It had in fact been solved in the 80s. Unfortunately, today people have forgotten that lesson. So there are a zillion startups which are again solving the 95% of the problem. Everybody can do a demo of driving a car on a freeway on a nice, warm, sunny day. Everybody can do that, okay? People could do it in 1980s with computers which were a million times slower. I'm not impressed when you do it today, okay? I'm not impressed at all, okay? So this is Dickmann's talking about what would be needed for the full version of the problem. And he set up this kind of a very complicated diagram, which is that you really need to, the inner loop is of course this lateral and longitudinal control, but in the big picture, you really have to assess the situation, predict the state. Essentially, you have to have a theory of mind for all the other drivers, for all the pedestrians, and this complicated looking bubbles and arrows is all about that. Okay, he never realized that system, okay, but this is what he thought was going to be necessary. On the other hand, if you wanted to make something work and show up in the New York Times, this is what you did. This is an example of a neural network from 1989, Dean Pomeroy. So this is CMU work. And this was a network which had, it's pretty amazing, 29 hidden units, 45 direction output units. It had the insight of Dickmann's that all it needs to drive a car is lateral control. You know, either you're too much to the left, too much to the right, stay in the middle. Network has to solve a little regression problem, or in fact it was quantized in some way. And it's amazing, look at these numbers. I mean, today we would have millions of these guys, but at the end of the day, that's what was the setup, and you could do it then. This is Alvin. Then in the other projects going into the 90s, so they in fact had this great demo of going all the way from Berlin to Paris. In the US, there was Lukma No Hands project, which is driving all the way from the East Coast to the West Coast. The CMU people did that. And then there was this great demo which happened in 1997. We took part at Berkeley. The PATH project here was very active. And then somehow we realized what the issues were. We realized that partial autonomy was not so easy to work with, because if you have, you let the car drive itself, but suddenly you need the human input, and the human is at that point asleep. What are you going to do, right? If the human is not paying attention at that point, what are you going to do? So, so effectively what happened is that at that time it was all being driven by the federal government. The car companies had come in and they had funded us, they had given us the cars and all the rest of it, but they didn't think that immediately this was going to work, and sort of funding kind of dried up, and people like me decided that instead of spending more time incrementally improving things, I would rather go off and work on other problems, which was the smart choice, because at that point machine learning was coming to the fore and problems like object recognition could be worked on, and we made great progress in the last 15 years on this. I'll just give you one or two slides on the kinds of papers we wrote back in the 90s. How do you do vision-based lateral control? So there's a problem of staying in your lane. There's a problem of not hitting the car in front of you. So you can do them both with vision. There are some interesting things, because at that time we were dealing with quite slow computing devices. So there was always going to be a delay introduced by the computing time. So you had to take that into account. Now control theorists know all about this. And delay, if you don't take it into account, will cause bad things to happen. but you can incorporate that into your observer and so forth. And there were various projects, and so there was, we modeled the car dynamics. This is a so-called bicycle model. You have these terms corresponding to the mass of the car. It's very good old control theory kind of stuff, okay? And I'm not going to go into more stuff here. So, so we could, here were the kinds of experiments we could do. We could do these experiments on how closely could you monitor lanes. How well could you stay in the middle of a lane? And even at that time, what we found was, at that task, machines were much better than humans. So there was a demo that we had, which was, there was a very curvy kind of path, and on that you had some cones, traffic cones, and the objective was to steer through the middle of that. And you try to do it yourself in like very quickly you're going to bang into one of the traffic cones. And this car could just smoothly glide through those curved trajectories, because that's the kind of a thing that a machine can do well. It has access to all the information, it has to plot out the optimal control, and it will defeat any human at that task. So that's history. So now let's come to where we are today. What happened is I put on the wrong thing. Okay. So what can computer vision do today? We are very good at certain problems. We can do object detection, etc., very well. But problems such as prediction and anticipation, we are pretty bad at. So in this picture, all the geometric parts of the problem, the recognition parts of the problem, we can do well. But when it's about anticipation of what's going to happen next, we are not so good. Let me give you another example. In this situation, you want to understand this scene. The most interesting question is, whom will this player pass the ball to next? Right? This is about understanding the behavior of different entities. And there is a very classic paper on this going back to 1943 from Kenneth Craig, The Nature of Explanation. It's about mental models. And what he said was that organisms need to carry around a small scale model of external reality, and that in that model they can do simulations, plan, and that's a safe way to plan as opposed to really always having to do things in the world. This insight really is, I think, behind the development of cognitive science in opposition to behaviorism, as well as control theory. If you think about Kalman and state space and so on, you can think of that as a formalization of this idea in a certain setting. Now, what has been responsible for AI successes? A lot of external supervision, but I will give this as an example. We have succeeded in getting these object recognition systems to work by lots and lots of examples. So zillions of examples. The mother says to the child, here's a zebra, and says this for 10,000 zebras. Is that what happens? No, that's not the way we train. This excessive supervision is not the way children train. How they are trained is really by this process of development, where for a large part of the exercise they are in fact experimenters. They are like the scientist in the crib is the title of a book by Alison Gopnik. So this child is poking around doing experiments. And this self-supervision is what enables the child, when somebody learns to drive at the age of 16, they are really visual geniuses. They have got a model of this external world. They've got a model of the behavior of people. If I'm driving on a road and then at a crossing, if there's a child, the child might run across. There will be certain people whom I expect will follow the law. There might be some drunk who might just stagger across. There are many, many different behaviors that happen. And these are to do with we learn them. We are visual geniuses by the age of 16. So it's that person who is being taught driving. On the other hand, what we are doing now with our car driving systems is that we are training idiots to drive, who are like idiot savants. They only know about driving. Okay, I think I made my case, so I'll let my colleagues continue. Okay, I think you can sit here. Huh? Yeah, I don't have to.
I had to borrow Anca's laptop, unfortunately, so thank you, Anca, for that. So I think Jitendra gave a great historical context to autonomous driving work at Berkeley and elsewhere, and I want to go into some of the specific details and projects we're doing in my lab, and also in the Berkeley Deep Drive Consortium, which is one of the exciting new research centers associated with Bear and the AI research faculty here at Berkeley. And I'm not going to give an overview of Deep Drive. Many of you are already sponsors, but if you're interested in the projects that we're working on, please take a look at our website, bdd.berkeley.edu, and Jitendra and Anca and I are all PIs in that center. So I wanted to talk about recent work in our group on how do we learn using deep learning how to drive. And there's really two different paradigms that I think are everyone's focused on right now. One paradigm is, and both of them involve computer vision. And I think what I like about Jitendra's talk is it reminds us there's been this long history of autonomous driving as a core computer vision challenge, and it's come and gone in terms of being at the forefront of where exactly the researchers are focusing their attention. I think it's very much at the forefront right now. And I think I won't have time to talk about it really in my talk now, but I could maybe during the Q&A get into how I really think it's an AI complete problem, right? I'm going to talk now for the next 5 or 10 minutes on low level, kind of how do we actually drive almost in a reactive way. But then Anca's going to step up and talk more about how we have a multi-agent perspective in driving. And if I had time, I'd also say ultimately we think there's going to be language and explanation and really traditional AI concepts involved. So to us, driving really is, at least to me, it's AI complete and exciting, although there's lots of low-level problems to tackle as well, and that's what I'm going to address now. And as I said, there's sort of two paradigms. One paradigm is vision is just for state estimation. And I'm happy with that paradigm because it's a really interesting state estimation problem. Like, how can we sense everything in the environment that's relevant to a driving decision? And as Jitendra said, I think it's hard to really bound that. And clearly we want to understand the road, the cars, the pedestrians and whatnot, but really we should understand the intent of almost everything, every agent in the environment, and that's a rich problem. And our perspective at Berkeley has been to focus on this new, revisited class of deep learning approaches for these problems and large-scale data sets. And I'll explain that in a few moments. And at the same time, there's the second paradigm, which we're also invested in, which is let's actually see if, since deep learning has had such a revolution in vision, and roughly the idea was let's give up hand-engineered feature representations and optimize jointly over the entire representation. I think a lot of people are conjecturing this is also going to be true for end-to-end control, and driving is an instance of end-to-end control. So shouldn't I just learn how to react, learn how to control a vehicle, learn how to move just from watching video and examples of how people do it? And so that's the second project that I'll talk to you about, which is the forget about internal representations, let's just learn about a driving policy end to end. And in both cases, our leverage here is going to be a very large-scale data sets and doing it generically across a large set of vehicles simultaneously. So just backing up to a slide of motivation, we know AI is quite successful for all of the reasons cited here and before. I don't think this video is going to play straight up here, so I'm going to exit out of the presentation, switch to the other screen, and continue to play it from here. It's just a bit of humor, and I apologize to our Volvo colleagues. Look, it works really well. Excellent job, except when it doesn't, right? There's still some, whoa, sorry. So we'll score that as a partial success. All I'm using this video for is just to say, you know, some things are working quite well, and some things are still, you know, a work in progress. And what is what characterizes the work in progress? And one of the key themes that my research group has been focusing on for the last several years, well, I think I would say that if you have enough training data, this new class of deep architectures really does work. And if you have that training data from the particular environment, so I'd speculate that that vision system, if it was a deep learning vision system, if it wasn't, then that's the problem. It should just be replaced by a deep learning vision system. But if it was a deep learning vision system, it probably was trained on images that were mostly frontal. And it wasn't necessarily trained on the side views of the pedestrians. Or more generally, we may have a lot of training data in certain domains, but not in a new domain. Like we may have a lot of training data from sunny Mountain View, but not so much from snowy Boston. And so we would like our systems, we know they work well with current deep learning architectures in a fully supervised fashion, but how do we adapt them to new domains? How do we have some, ideally, performance guarantees? That's still future work for us. But how do we do the best job that we can when we encounter a new domain, even when there are no labels in that domain? So that goes by many different phrases. We call it a domain adaptation problem, typically, but there are other names for it. And it's often, it's very related to transfer learning and metric learning. And in the context of driving data, we are very happy to have large data sets in our BDD center provided by our partners Nexar and Mapillary. And we have large-scale data sets, both video and stills, and annotations that we're collecting on them to try and identify driving relevant objects in the scene. And this follows what is, I think, basically one of the standard tasks in the field right now, which is in vision for autonomous driving. This is the semantic segmentation task that was defined by colleagues at Daimler. And using state-of-the-art convolutional networks to predict the class label of every pixel. So this is sort of the ultimate state estimation problem. At one level, for every pixel in the scene, please color it with the identity of the object in the scene. It's also, you know, one of the ultimate computer vision problems, which is why we like it. And as has been shown by using the state-of-the-art FCN, means fully convolutional network. That's an architecture that we developed in the last few years here at Berkeley. If you have ample training data and testing data in the same environment, everything is pretty good, and that's what's gotten a lot of people excited. But as we show and experience recently, and probably many of you do in your labs as well, things still aren't perfect when you go and collect a new data set, perhaps in a slightly different environment. Here we have dash cam data from San Francisco as part of that new data set that I mentioned. And it doesn't necessarily do so well. It's, you know, hallucinating a car in the upper left in that tree. It's missing, it's seeing a car in the front there where there's no car. And in some sense, this isn't too surprising, right? The Cityscapes data set is very idiosyncratic, and this model had only been trained on the Cityscapes data set, right? The Cityscapes data set doesn't have any streets that are this wide. And in fact, it's all collected from a single vehicle, and that vehicle has a hood and a hood ornament basically in the same position in every frame. So it gets confused in the bottom. And the appearance of signs is different in Germany than in San Francisco. And worse, there are no tunnels in the Cityscapes data set. So when you take a stock cityscape FCN model and run it on a frame from a tunnel, you get garbage. And the current model doesn't tell you that it's garbage. It just tells you, here's what I think it is. And it doesn't adapt to the environment. So the research agenda that we're pursuing right now in our lab is building models of this form, but which provide confidence and estimate and a notion of reliability in a new domain. We are, stay tuned for those results to be forthcoming soon. But what we have been showing and continue to show is if you have unlabeled data in a new domain, how do you do the best job that you can on classification? So I'll go back to some sort of classic slides and paradigm here that's showing this formal problem statement of domain adaptation, here not necessarily in the driving domain, but just recognizing generic objects from the internet. If you want to recognize ImageNet categories, you can use nice, clean ImageNet images or images of products that you scraped from Amazon in this example. But then when you go out into the real world, you find that the camera on your agent, either a vehicle or a car, a UAV, or just a person walking around, often takes images with lighting conditions or viewpoints or pose bias or photographer bias that's significantly different from what that training data was. And so you're in a bit of trouble. And so the question is, how, without any labels in a new environment, how do we do the best job we can? And that's the domain adaptation problem. Because if you just train a network, here I'm illustrating a network as that convnet of boxes in the top row, and just train it on one data set, test it on the other, you can get very bad performance, and I think all of us have seen that. So this is not obviously a completely new problem, and if you have labels in the target domain, it's straightforward what to do. If you just have additional straight-up labels as to what objects are, you can fine-tune your network, and that's a well-understood adaptation step. Or if you have even more powerful information which says this particular backpack is what is in this domain and the same backpack is in this domain, now we have a very nice metric learning problem, and we and others have published models over the years, and it's well known it's often called the Siamese network for doing that kind of metric learning in a convnet. So you would optimize your network to project both images to the same feature point. But I said we have no labels, and we certainly don't have paired instance constraints, because they're very expensive to obtain. What can I do just in this general setting where I have a notional data set of maybe trying to distinguish cars and pedestrians or bottles and phones, and I can train a classifier, maybe a convnet, to distinguish them. But I have my new data, and it's pretty far away, and in fact, the inter-domain distance, even in a pretty good feature space, probably will dominate the interclass distance, and that's a bad thing. So the basic notion that people have been working on for over 5 years is, if you know nothing else, you should try and align the statistics of different domains. On average, you should find a representation in which your data distribution looks the same. You might want to align the moments of your distribution, or even more powerfully, you might want to say, I shouldn't be able to tell the difference between my domains in my representation, and that's often called discrepancy. So we want to actually minimize something called the discrepancy, and it operationally means we want to not be able to train a classifier to tell the difference between the two domains. So we've called that domain confusion in recent work. So it's an alternating optimization problem where we try and simultaneously learn a classifier for the source domain and update the representation so that I can't learn a classifier for the domain distinction. And that sounds difficult to optimize, and it is a little tricky, but it does work in practice. And many other labs, including our own, have been showing results recently on this. So ultimately, you get a representation where you hope the domains are confused, so you don't care whether you're getting data from the source domain or the target domain, but you can still classify the target. And the most recent version of this that should be on archive right now, I'll refer to Eric Zhang, and Judy Hoffman's now a postdoc at Stanford. And the key idea is we've extended this architecture to have sort of very state-of-the-art components, including a GAN loss. And this overall family of adversarial domain adaptation is similar in spirit to recent generative adversarial networks. And any of you who are interested, I'll point you to our new ADA algorithm, and that should be on archive, or you can email me or Eric to learn more about it. We basically can pre-train on one source task, adapt using unlabeled information in the target domain, and then run on the target domain images. And it works well in many cases, going from MNIST digits to Street View digits, going from one modality like training on intensity images to testing on another modality like RGB. And getting back to the point of this talk, it works well on this sort of benchmark standard task of semantic segmentation per pixel in automotive scene labeling using fully convolutional nets. And so that recent innovation is to take these domain annotation ideas and bake them in at the fully convolutional level so that every pixel, the classification decision is being made and informed by this, this adaptation. And indeed, we can now, in some synthetic cases, we get some very nice anecdotal results and quantitative results. Here, if you're training on, oh good, you can see this. Here, if we're training on these images that's in one weather condition, and since it's a simulated environment, we can get the exact same images in another condition. We could use paired data here, okay, but we're not using the pairs. The ground truth should be the final column. And here we have, if you used a stock model trained on fall and tested on winter, and then with our adaptation, it can definitely overcome this type of appearance variation, again, without any labels in the target domain and without any paired instance constraints. And this is also bared out in real-world data. The results are still a little more subtle. I'd like to emphasize this is a completely generic algorithm that has no prior knowledge of driving. So there's a lot more knowledge that we could put into here to further clean up these results. But things improve, including the example that I showed before. Still work to be done, but there's a lot less noise in the scene. So I'm kind of moving forward. I need to save time for my second part. If you're interested in this, please look at our archive. Because I really wanted to now, so that if you think of vision as state estimation, well, all of this has been relevant. We have this enormous data set of hundreds of thousands of hours of driving data. We can use that to explore domain adaptation and prove robustness across a wide range of driving conditions for tasks like that semantic segmentation task, certainly also just bounding box prediction if you care about that. But probably a little bit more exciting is just solving the end-to-end problem of the task. It's a little more radical. Can I just forget about hand labeling anything and just train a network to mimic how people drive? And as Jitendra said, that's an old idea. He had the same version of the same figure. Dates back to the earliest convnets. Jan LeCun's work was in '88. This Alvin work was in '89 at CMU. Even back then, they realized, hand writing a computer program to figure out what pixel patterns are a lane marker or not in general natural conditions is probably pretty hard. Learning those patterns from data is a better way to go, even with a very, very limited neural architecture, such as the one that they used. Fast forward to last year, and the same idea has been reinvented and strengthened by the work at NVIDIA, probably very famous to many of you. Still basically the same idea, but with a higher capacity network, a little bit more of an idea how to train with jitter and pose variation. Although we'd have to point out that the original Alvin paper was pretty sophisticated. It didn't quite have domain adaptation inside, but it did have the idea of training on synthetic data and transferring from a simulator to real world, a lot of ideas that we're still working on today. And many other groups around the world have been discovering that you can actually just do this almost at a hobbyist scale. And at Berkeley, we've been very fortunate to have Carl Zipser, who I think is in the audience today, developing a whole fleet of RC class vehicles which have the same kind of per vehicle convnet architecture where you directly train the network to sense, perhaps just using a low-res black and white camera, and then predict in a new environment after being trained from human demonstration how to turn on Berkeley streets here. And I think the surprising thing is how easy certain kinds of lane following really is, even with a very basic convnet. This one is much similar to the original Alvin network than the more powerful vision networks that we're used to and what we saw in the NVIDIA work. And not only is there sort of a single agent paradigm here, but with a fleet of these vehicles, which you can deploy. Each one of these essentially has a Jetson TX1 or some similar tablet class architecture on board. You can now have crowd driving behaviors. I believe these agents were all trained individually, but still managed to do collision avoidance collectively. But I'll refer you to Carl if you're interested in that project. And Carl, where are you? Carl's in the back there. You can talk to him at the end. And so in my group, we're collaborating with Carl and independently also trying to generalize this problem statement from what has been done by Carl and by NVIDIA and by Palmerow in 1989, learn a single end-to-end controller for a specific vehicle. My conjecture is that really envision whoever has the largest data set wins. And while I love every sensor that I could possibly put on a vehicle, we usually discover that if you have 1 million training examples, you do much better than if you have 10,000. At least when you're trying to do something that involves state estimation and natural scenes. And so I want to see, can we learn an end-to-end driving policy from the largest possible data set I can imagine of actual driving, and that comes from crowdsourced dash cams and partners like Nexar and Mapillary, as I mentioned before. And so that's what we've been doing. I only have time to give you quick highlights here. The key idea is to not think of it as predicting the vehicle-specific actuation, but instead let's try and take video and predict the generic future motion, predict the future ego motion of the vehicle, predict how the driver caused the vehicle to move. We have that data because the dash cams we have are from iPhones, so we have IMU data and GPS data. We can also do visual odometry. And it's a pretty standard architecture, although ours has some innovative aspects where we take video as input, perhaps also take the ground truth IMU, but we don't need that. We can also just run it just with video as input, run it through a recursive, fully convolutional network architecture, optionally side train it on pixel labels in a privileged training paradigm, but mainly predict the future ego motion of the vehicle, and most importantly, leverage very, very diverse training sets. And we're not doing any domain adaptation here, but we will soon. And we can then show that at least for held out data in our data set, we can predict that the true driving motions have high likelihood. Now, this is not actually driving the vehicle yet. Stay tuned for that. Then I'll call it an actual policy. Right now, I'm just going to call it a driving model, like a language model, and that it explains with low perplexity all the data that we've collected. And we have a lot of data, so it's pretty exciting. And we've seen the other models that are trained on a single vehicle can go ahead and do that. So I'm just going to steal an extra minute and show a little bit of this video, which shows we have 2 sets of experiments in our paper. There is an archive you can look at, where we first just try and predict a few discrete actions of go straight, stop, or turn. And the red bars show the ground truth, and the green bars show our prediction. And it's getting it fairly well, and we have some, this is still a work in progress. And I hesitate to say whether it's how exciting it is, how much of the problem this solves right out of the box, or to point out how much of the problem isn't solved. And I'm not going to go put my son or daughter in an autonomous car powered just by this algorithm quite yet, but I think it's a really exciting part of the final story. I'm going to jump ahead to the continuous prediction task, if I can. I don't know how I do that with this interface. Well, I might just have to let it roll and say, so what is conceptually exciting about this is we do not rely on any hand-labeled information to decide what intermediate features to pay attention to, either for state estimation or for end-to-end control. And at least anecdotally, my students believe this model discovers the distinction between different traffic light colors. And that's not something that's ever been annotated to this model or in any of the data that it's seen. And these are true even in the version of the model that's not side trained on cityscapes data and the like. And the second part of this video, which I'll let play before I stop, will show you the continuous version of our experiments, where we predict the distribution of allowable angles that the car could take, and we show where the ground truth motion was and what the peak of our predicted distribution is. So here, I think the red is the ground truth, and the green shows our distribution over possible directions. And we're also predicting speed, but not visualizing it here, I think. Okay, so that gives you, I think, a pretty good sense, and I've used more than my 15 minutes. So I'm just going to show you that we have an archive, and I think I'll happy to take questions about this during the Q&A. But now I can hand over to Anca, who, so I've basically told you about the nitty-gritty of how are we going to learn kind of what I would call low-level or mid-level controllers. And a very good question is, especially as vehicles interact with autonomous vehicles interact with people, how do those vehicles understand what the other human drivers might be doing? Or how do they solve problems that aren't just kind of near-term and reactive, but require a multi-agent plan? And so Anca will tell us about a theory of mind for autonomous cars.
Thank you, Trevor. Hi, everyone. Okay, so some of you might remember me from last year because I got a chance to share a little bit with you about our work on how to model how people might infer a robot's intentions and use that so that a robot, like a personal robot, in a collaborative task with a person could actually be intent expressive. And today I want to share about a slightly different problem where you no longer have cooperation, right? So driving is the kind of problem where it's somewhat cooperative but not fully. Where instead of focusing on how people infer intentions and so on, we're going to focus directly on what people actually do and a model of their actions. So typically in driving and what we've heard so far, we'd like to focus on how we can get cars to reach their destinations while meeting task constraints, not the least of which being actually staying on the road. The kinds of problems that I like to think about are actually problems where the car isn't doing this in isolation, but it's working in a world where there are people, right? So for instance, other vehicles that are driven by people as opposed to by autonomy or pedestrians or things like that. Now, typically when we have problems like this in driving, what we do is we say, well, the first thing you'll notice is that it's not a really good idea for the car to actually collide with the human-driven vehicle. So we're going to think of this as an obstacle that is moving, and we're going to try to estimate how it's moving, where it's going to go in the future, and try to stay out of its way. So that gave birth to the main paradigm for interaction that we're using now in driving, which is interaction as obstacle avoidance, where I'm going to come up with some sort of probability distribution over what might happen in the future, given the current state, for the person and for this obstacle that is moving, and then I'm going to write down a utility function or some set of constraints that say I have to stay out of their way. And there's many ways to do this, from simple Kalman filtering to sophisticated ways that actually leverage previous data. This is an example from Brian Ziebart, and it's not in driving, it's in navigation. But you can see here how, as a person is moving, this algorithm is forecasting what they're going to do in the future. So this is interaction as obstacle avoidance. It's a very useful thing to do. Here's an example from human-human interaction where it goes terribly wrong. This is a kind of a tough video to watch, but there's a truck driver cruising along at constant velocity on a highway. This car just merged in. This car's going to try to merge in. They put the blinker on, but the truck driver just keeps going. Just like, yep, you should get out of my way. I'm just going to keep doing what I'm doing. And, you know, each of them keeps on insisting, I guess. All right, so this is an example of interaction as obstacle avoidance gone wrong. Very clearly, this car is not being very good at staying out of the truck driver's way. So you might look at this and think, well, okay, interaction as obstacle avoidance is a really important paradigm. But, you know, and that's what I thought first. And the more I looked at this and the more I watched it in slow motion and so on, I came to the conclusion that it's also an argument against interaction as obstacle avoidance. And this might sound a little bit surprising, but here's the thing. How many of us would actually behave like this truck driver is behaving? I mean, maybe some, right? But for the most part, most of us will actually hit the brake and let the person merge in. We do this every day. And yet, when we're telling our cars, here's an obstacle that's moving, stay out of its way, we're essentially implicitly modeling people. We're telling our cars to model people as behaving as if they're this truck driver. And that's physically safe, but it deprives these autonomous cars of this core aspect of interaction, which is the actual ability to coordinate with other agents that you're interacting with. And this has consequences. This is an article that I read actually a couple years ago. And it's from, it talks about an incident that Google had where it got stuck at an intersection because human drivers kept on inching forward into the intersection, and the car, which is programmed to stay out of people's way, would just stay there and let them go, right? And then driver after driver after driver got to go, and then the car was just staying there. And this is not what we do, right? Like at intersections, I inch forward and then other people stop. I don't wait for everyone. I drive on the Bay Bridge because I actually live in San Francisco. And I have to do this every day. I have to go in front of someone. Otherwise, I would never get to take an exit, or I would never get to enter the bridge, right? So yes, it's not what the book might actually say, because I don't always have quite enough space, but I rely on this person actually braking and giving me a little bit of space. So whether we want to or not, robots will take actions, and these actions will actually have effects on what people do. We see this every day. Not everyone's going to act like this truck driver, and we thought that accounting for these effects that robot actions have on people's actions is actually a pretty important thing to look at if you're going to do autonomous driving. So that's what we did. We started looking at a model of interaction, not as people are obstacles that move that we need to avoid, but something that I like to describe as an underactuated system. So an underactuated system is this thing from controls. An example is an inverted car pendulum, where what you're trying to do is you're trying to get this pendulum to balance, but you can't directly actuate this joint here. So this moves, but it moves as a consequence of you pulling on this, right? So you get to move the cart, and you have to move the cart in such a way that the pendulum balances. So what's important about an underactuated system is that you can actuate some degrees of freedom, but doing that has effects on other degrees of freedom that you don't have a direct actuation on. And we think that not for all interactions, but for some interactions, this is a pretty good model. We're going to have these cars. We have direct control over what their actions should be, but kind of whether we plan for it or not, these actions are going to inevitably influence what the person's actions end up being. And so the way we've been thinking about this so far has been to say, we don't know what people will do as a response to what the robot does, but maybe we can borrow a little bit from the principle of rational action and say that approximately, not exactly, but approximately, there's going to be some utility function that we're going to call UH that sort of explains the actions that people are taking. I mean, ultimately, they're trying to avoid collisions, they're trying to be efficient and so on, and they're doing that in some way. We might not know exactly what that way is, but we think that it might be explainable as the approximate optimum of some utility function. If we had that utility function, then we could go ahead and form a probability distribution over what the person might do, not just conditioned on the state, but explicitly on what the robot is doing. And then the robot could use this to decide what it should do. The robot could search for its own actions to optimize its own utility, but taking into account this probability distribution over what might happen as a function of the actions that it's choosing. We don't know what this human utility is, but we get demonstrations, right? We get to watch people actually drive around other agents and see what they do, right? And we can try to backtrack a utility function either offline from a bunch of data from people that we then use as our model, or online as we're actually observing a new driver. So here's a little bit of what happens. By the way, I should say, a core part of this work was to actually formulate this, but a really huge chunk of work was to actually figure out how the heck to actually approximate this in order to do real-time control. But the details of that are in these papers. So here's what happens when you do that. The first example that I want to share with you goes back to the kind of Bay Bridge situation. And it's an example that we calculated based on a offline learn model of human driving that the robot is now using. So here's the robot, here's the human car. The robot needs to take an exit on the left. And what would normally happen is if you treat people as obstacles, the robot would realize that it doesn't have time to merge in front of the person. It would brake and merge behind. which is fine if there's actually someone, if there's no one behind, but if there's someone behind, then that's not really a good thing, because you just stay there forever. That's not what our car does. Our car actually decides to merge in front of the person because it knows that the person can brake. Not always, right? That depends on the person's current velocity. It depends on how much the person will need to brake and so on. So that was the first thing where we saw, okay, we're actually getting a little bit of coordination. We don't have purely ultra-defensive cars anymore. We have cars who have at least the ability to be aggressive. They don't have to always be aggressive. It really depends on what utility function we give them. And then, of course, this wasn't the end of the story because we looked at this video in the beginning of the talk, right? And we saw how this truck driver behaved. And so we know that not everyone will brake. And that teaches us that relying on an offline learned model of people and assuming that as the model, even if you replan at every step, might not be the best thing to do. And so where we went to next is figuring out how to actually online learn this from user data. You don't have a lot of interaction with the person. You don't get to observe the person too much. So you have to be pretty clever about leveraging the actions that you can take as a robot to gather the kind of data that's actually useful for you. So here the robot is, again, optimizing its utility function, but also trying to leverage its actions to gather more information about what kind of driver the person is. What we found with this kind of algorithm is that the robot actually decides to just kind of start nudging into the person's lane, not necessarily committing to a merge. And this is useful because this is the kind of probing action that will enable it to determine, for instance, whether the driver is a more aggressive kind of driver, prioritizing efficiency more than safety in their utility function, or vice versa, or whether the driver is paying attention or not, and things like that. So our car kind of inches forward in this type of situation, and if the person brakes, then it updates its model of the person's utility function and decides to merge in front. And if the car doesn't brake, then it updates its model of the person and decides to not merge in front, which is the kind of nice kind of interaction that we'd hope to see. So this is all nice in theory, and this is all based on data collected from people on highways. We also try to put this in not a too realistic setting, but at least use real people and not just our simulated people that follow perfectly the model that we learn. And so we ran a user study, and my favorite examples were not actually on highways. My favorite examples were at intersections. So we go back to the sort of this somewhat difficult four-way stop situation where you get into this do I go, do you go, do I go, do you go kind of mode. And so what happened here, so we ran the study, people interacted with these cars at intersections, on highways, and so on, all in a car simulator. And then we looked at what happened. We plotted the person's trajectory over time and the robot's trajectory over time, and it deferred whether we distracted the users or not. We distracted users by giving them a cell phone. Turns out that's pretty effective. So that led to different driving styles and making sure that we get different driving styles in the population. And what the robot did was really depended on that. The robot, of course, not knowing that we gave people a cell phone. So here's what these graphs actually mean on the actual scene. So the car, this is again the autonomous car, the car decides to inch forward, which I thought was really cool. The car decides to inch forward, it sees if this person will brake and stop and let them go, and if so, it will update its model and it would decide that the best action given this new information is to proceed. If not, if the person doesn't brake and keeps going forward, then it will actually back up and let them go. So that's what the car does. Again, very interesting kind of coordination behavior. And then finally, this is my favorite example. We also played around with the notion of not giving the autonomous car a utility function that says be efficient, but giving the car a utility function that explicitly targets an effect on the person's actions. So in this case, we looked at, can we resolve explicitly these coordination situations by, for instance, telling the car to get the person to go first, right? So a very polite car that tries to make sure the person goes first, but as quickly as possible, right? Not wait and play the whole coordination game. So in this situation, what the car decided to do is actually to start inching backwards. And this was really surprising. No person does this. It's actually fairly expensive to go in reverse, and even if there's no one behind. I've seen pedestrians do this, though. I've seen pedestrians at crosswalks, sort of, if there's a car that wants to turn and they're caught up in something, they'll actually take a step back often from the intersection. So I've seen pedestrians do this, but not human drivers. Nonetheless, this is what our car decided to do. And it's kind of, in retrospect, it makes sense because that's an action that then makes it much safer for the person to go through and therefore increases the probability that that will happen because the person is honestly just trying to optimize, between, okay, how do I stay safe but also am efficient. And this sort of thing we found, I'm not going to bore you with the details, but we found that it actually works with people and that consistently we're seeing the kind of behavior that we expect, at least significantly more so than when we treat them as obstacles. So to me, this is really exciting because, like Trevor said, it relies on kind of a little bit the beginnings of a theory of mind of other drivers. And out of that, without having to hand code any particular strategy, without calling the user experience group and saying, okay, what should I do at intersection? Should I inch forward? How much should I inch forward? With what velocity? But what in this other kind of intersection, what should I do? And so on. We just have the car figure all this out by being a little bit smarter about the way it's reasoning about people, right? They're not just obstacles, and if they're not just obstacles, they're actually agents that make decisions. We actually start seeing that these coordination behaviors that normally we have to hand code start emerging out of the optimization, out of the car's decisions. So again, I think all of this is based on modeling interaction and specifically reasoning about people and how their actions will be influenced by what robots do. And this is the kind of thing that we're seeing to have applications not just in driving, but in collaborative manipulation types of tasks as well. And with that, I'd just like to mention that Dorsa Sadiq is the main student responsible for this work. And I would also like to thank all my colleagues at Berkeley who helped me with all of this. And now we can start the panel and actually answer questions. Thank you. And I would like to say that I took exactly 15 minutes, let it be noted.
I think there's a microphone in the back of the room for questions.
Yeah, we have two running around.
Otherwise, we'll have to interpolate or hallucinate questions. There's a question in the front here. I see a microphone coming.
Hi, yes, thanks very much. That was really interesting. I have a question. It seems like a lot of the problems that you have faced with the autonomous driving is because you have to interact with these unpredictable things called humans. So I'm wondering if you took that away, if you lived in some fantasy world where all these self-driving cars were driving because they're all autonomous, how much easier is the problem and how much quicker could it be deployed?
We'll still have pedestrians.
Yeah, I mean, I should mention that the project at Berkeley in Path in the 90s was about using platoons and so forth. It was all about freeways, but the primary focus there was to increase the capacity of the freeway. And the fact is that, under normal traffic conditions, a lane you can only have a capacity of something like 2,200 vehicles per lane per hour. And that's to do with human reaction times and so forth. If you have cars under computer control going behind each other, effectively they're forming a train. You can have a capacity of 8,000 vehicles per lane per hour. So imagine that without building any more lanes, the capacity of the freeways would go up by a factor of 4. But it relies on the system that these vehicles are communicating with each other and they are willing to be subservient to sort of commands from other vehicles and so forth. And now I don't know whether that fits in with American self-independence.
We've got one back here, sorry.
Hi, I would like to thank the panel for the excellent presentations. I also have a question. There is talk about fully autonomous cars. There is working and interacting with human drivers. But I think perhaps a more feasible solution would be shared autonomy, where we would be perhaps more willing to have our children in such a car. Because in the shared autonomy, the machine intelligence can make up for the missing intelligence in the human driver, the blind spots and the fast reaction of the machine. I'd like to know what you think about that. Thank you.
Yeah, I think that's a great idea and an intermediate step towards full autonomy. Many of the perception tasks for driving assistance systems are stepping stones towards full autonomy, and what consumers ultimately want, I'm sure there'll be a diversity of desires.
The one thing that I will caution is that it's actually fairly difficult for people to take over command on short notice and figure out the right thing to do. And I think assuming that that can happen in the same way that we can fix mistakes when we're the ones driving and we've been, I think I may turn my microphone off and that will help. Okay. Assuming that that will work in the same way as when we're fixing our own mistakes while we're actually actively engaged is probably a fallacy. And so that sort of suggests to me that we can add more and more autonomy and we'll see that overall safety goes up to some point where it will start actually declining, right? So I think we have to be careful about that. Then I think we have to be careful about people who, if there is a blind spot detector that is fairly reliable but not 100% reliable, over trusting it. And I think we have to be careful about people not having the right mental model of what the thing is capable of, what kind of situations it can handle, what kind of situations it can't, and so on.
In the last talk, the last section about interaction, the way the robot interacts with a human-driven vehicle is totally different from how two human drivers would interact, say at an intersection. A lot of times people would wave at the other guy, say go, right? So if we're not taking this, is anybody using this kind of information? Because we seem to be dropping a lot of very crucial information from the analysis altogether.
Right, absolutely. An autonomous car unfortunately can't, right now at least, wave someone by or make eye contact and so on, right? And these are very useful coordination channels. Well, people have suggested using some artificial channels like text and lights and things like that to get around this. And I think one of the challenges with that is with artificial channels, it just takes our brain a little longer to process that and to get adjusted to that. So this is why we've explored the car's physical actions as a channel for essentially communication. It's not directly communication. The car isn't trying to signal anything, right? But the car is trying to actually reason about its effects on the human driver. And out of that sort of beautifully come these behaviors that we might interpret as coordination behaviors. But I think, to your point, physical actions, I think, go a long way. We can't help but make inferences about other agents based on the actions that they're actually taking, and I think that's an important thing to figure out. But I think we should be exploring other channels as well to the best of our abilities, and I don't know what those interfaces might look like.
I've got an observation and a question. The observation is about truck drivers who are operating with a completely different optimization function. They're sitting behind an engine about the size of a muscle car that can't get them up hills, and they're trying to save on gas because they don't want to lose any energy and momentum. Their optimization function is what causes them to be on your rear bumper going downhill at 70 miles an hour. So they really do need to be modeled differently. And the question has to do with a whole probably 20 years of at the dinner table hearing about cockpit automation. and keeping the pilot in the loop. And as things got more automated, they lost the attention of the pilot. And stories like the UPS flight to Los Angeles, which had a pilot and a co-pilot who were supposed to be watching each other, and they both fell asleep and flew an hour out into the Pacific before one of them woke up. Cockpit automation is great, but Sully Sullenberger, if he had not had his hands on the yoke and his eyes out the window, never would have put that plane down in the Hudson. And I haven't heard any talk about what's changed. People, when they're asked about how good a driver they are, they're all in the top quarter or top half of drivers. They think they're not a danger, other people are. And yet they are the danger. So what's changed that we don't need to worry about keeping the driver in the loop so that they can take over? We seem to be assuming that we're going to have self-driving cars, and a lot of, since we have 35,000 people killed every year, we won't mind about the 20,000 people that are killed in automation accidents because we saved 15,000. And I don't think the public's going to buy that. What do you think?
I think they would buy it if it's 15 and not 15,000 people. I mean, I think at some, if there are 15 people killed in autonomous vehicles versus 30,000, I think the public would accept that. If it was what you said, just only 40% reduction, I agree with you, it might not be accepted. Yeah, I'm optimistic that we would.
But I think everyone's in agreement that in the meantime, before we have full autonomy, if we're going to adapt the shared autonomy paradigm, then we have to have the human in the loop discussion. And there was another question about that. Yeah, and I think that's actually really, really hard when you're disengaged and you have to re-engage, right? So the way these systems can work well, if is cruise control, for instance, I don't lose that much attention because I'm still actually actively steering the whole time, right? And so I don't have to deal with the pedals, but I still deal with the wheel. And I think that changes when I'm totally out of the loop for a while and then I have to be inserted into the loop. So I don't think anyone has a really good answer for that, but I think everyone is actually thinking about it.
Thank you, Professor Trevor Darrell, for mentioning the problem of domain adaptation. I think it's a very important problem. Without solving this challenge, it's really difficult to widely adopt all those fruits from training CNN. So there's another orthogonal problem of transfer learning. For example, we have all sorts of data sets, but not all those data sets are labeled equivalently. For example, certain data sets like Cityscape, it's a relatively large data set, but it doesn't have all the labels that I want. For example, if I have another smaller data set with all the labels that I want, do you have any ideas or suggestions on how I can combine them intelligently to get the best of both worlds?
I definitely would reiterate that as a very important problem statement, and both across modalities and across labels. It's important to have architectures that can not only predict a certain set of classes, but allow you to augment the model to have additional classes. And I think it's still a very active research topic, and unfortunately there's no individual model from my group that I can point you to. Except at a very high level when we start looking at how we can use natural language as a representation. So we do have efforts where we look at how you map an image region to a generic text string. And I think that paves the way to more general representations, although we haven't been doing that so much in the automotive domain. I'm hoping Jitendra has something more informed, more enlightened than that to say. Okay. Yeah, it is a very good problem, and we are working on it.
Thank you.
Yes, I had another question. So at the beginning, Jitendra, you started off with it, I'm over here again.
Oh.
So you started off with this discussion about how 30 years ago autonomous driving started, and it was going to be, you know, everybody said it's going to be here in 5 years, and 5 years, and 5 years, and here we are sitting today, it's not here yet. I didn't hear the other participants sort of give their response to that. That was kind of a very, that was your opinion. I think you were implying that it's not going to be here another 5 years either. So I'm curious to hear what the rest of the panel has to say about that.
And I think Trevor and I might have diverging points of view.
It depends on what you mean by autonomy. I think that's the standard answer. I think some forms of it are already here, and I do feel that interesting forms will be in the consumer market within 5 years, and it might be 50 years before every aspect of the problem is solved.
Yeah, I think with that version, I'll agree with that. My reaction was to what I see in the popular press, where a lot of it is driven by people who don't know what they're talking about, right? And so I'm coming at it. There are parts, this is a problem which has the characteristic that 95% of it is what we could do 1980s. And every 9 in this business, we are at 99, then 99.9, then 99.99, right? Those get harder and harder. And so if you can find ways of using what we have now, which I think we can do quite a bit, I think we'll win. And the secret is to figure out how to do that and how to use the human and the machine together. So what I would bet against is this complete autonomy of the type that the Uber taxi comes to your home. It does not have a human being in it. It takes you to wherever you want to go. That, I'm willing to bet, is not going to happen in 5 years. Okay, I'm willing to make that statement.
Separate lanes or a particular
Yeah,
region
with no modification of the environment and so forth, right?
For any pair of homes or for some pair of homes?
With high probability, shall we put it, probability 1 minus epsilon.
So I think there would be, for some pair of homes, or for going from Berkeley to Lake Tahoe on I-80, or at least Sacramento on I-80, in one lane, that I think something like that would happen.
See, freeway driving is actually the easiest, which in fact, when kids learn at 16, they do freeway driving later. They learn in parking lots. Whereas for cars, for autonomous cars, it's the other way around. Freeway driving is actually easy, and that was what was demonstrated on earliest. The nice thing is, I think in terms of research, we are now moving on to exactly these harder questions, which have to do with basically, as Anca described it, theory of mind of other cars. We are getting to the point where we are trying to model the behavior of the other agents in an interesting way.
I mean, I didn't talk about this, but pedestrians are important. And to your first question, right, that even in a world where we have full autonomy and in a world where we can perfectly coordinate these things and all the car companies kind of shake hands on communication protocols and somehow all of that works out, right? In cities, you'll have to deal with pedestrians, and I think these problems won't go away.
I mean, to me, it's a data question. If I have 10,000 examples of a previous trip on the same exact piece of road in the last 48 hours or 400 hours, I'm pretty confident, I think, that a very simple algorithm will react well. And so when we'll get that kind of data density is a systems question, but I would speculate that for certain aspects of the problem, we will get it sooner rather than later.
Jan has a question.
The opportunity be better if you have some form of coordination. Actually, we can have peer-to-peer communication between cars. We have global perspectives, right? You have a global picture that you can convey. So the combination between autonomy and some coordination type of function might not be better.
I mean, yeah, but the problem with that is that you still have to beam something to someone's brain, right? So I can see how autonomous cars can very nicely globally coordinate in a centralized way, and how that would work out beautifully, and it would save us a lot on traffic, like Jitendra was saying, with the platooning. There's already a lot of evidence for that. But when it comes to putting this on people and human-driven vehicles. That sounds challenging, right?
Sure.
There was a suggestion at some point that the car could get some message and then convey it to
That's
you as the
correct.
driver. But then that does introduce the sort of like, the car has to actually say, Joe wants to go first. Are you okay with that? And you have to say yes or in some way, right? And maybe when we have also BMI, that works magically well and things like that, right? That's what Jan wanted me to say, okay?
Okay, Carlo has a question, then that should be the last one.
So let's be a little bit conservative and assume it takes us 10 years until we have enough nines there so that the autonomous cars are like 10 times better than the human drivers. Then what? I then think we still have to face the societal, psychological, political, and insurance battle. And would we be willing to then let the autonomous car actually drive and take over, even though they might still cause 3,000 deaths per year? Or what would be our policy? The reasonable thing would probably be that we say, okay, at that point, any human driver who gets involved in any kind of car accident immediately loses the right to drive. Okay, so we get the weaker part of that population out. And that way, maybe we get more people then into the safer cars. That would be rational. I don't think that society would go for it. Or what's your feeling about this?
I mean, the rational behavior is clear, right? If there's we have from 35,000 deaths a year, which is what it is now, if we can lower it to, maybe the burden should be, we shouldn't be happy with 34,000 deaths. Maybe it has to come down to 10,000 or 15,000. But human beings are quite irrational. I mean, you must be, in the current climate, we've all read these stories of what are the risks from dying of lightning, a toddler shooting you with a gun, or a terrorist from one of these 7 countries killing you, right? And you know how the country behaves. So, sorry to bring politics into this, but we are not the most rational of people.
And that was the last question. So thank you for your question.
Okay, we'll reconvene in about 20 minutes, 2:45. We're going to have our last panel.
There's coffee in the back. Sorry.